Welcome to the lecture series conducted by CEC-UGC. I am Dr. Anuradha from Lady Shriram College for Women. I am here to discuss a lecture on continuous frequency distribution and arithmetic mean. In order to elaborate how to construct the continuous frequency distribution, I think I will start with an example on the onset. So let us look at our variable under study, which is the height of an individual. Okay. Now I have got 40 observations on this variable capital X, and we can see the observations on the screen. Now before I go on to discuss how to construct the continuous frequency distribution, it is better to notice certain points here. First, we must look at the minimum value that you have on the observations, and which is 120. You can see that 120 has been highlighted as yellow. This is the minimum value, and 150 is the maximum value. So I have to construct the continuous class intervals in such a way that we cover the entire range of observations, which is going from 120 to 150. So here the range is 150 minus 120, which is 30, and we have to construct class intervals so that this entire range is covered. When we construct the class intervals, we are going to construct class intervals of the equal width, because they are preferable, they are easy to analyze. And then comes the point, how many class intervals should I have? Now I should not have very small number of class intervals, neither I should have very large number of class intervals, because in either case my analysis will be completely disturbed. We must have some kind of optimum number of class intervals, which gives me the better representation of the observations. So therefore what I have decided is that it is completely up to the user to decide how many class intervals you want to make. So I have decided to go with a class interval of width 5, starting from 120 and then going till 150. So let us go to look at the figure here. So here the class intervals are 120 to 125, 125 to 130, 130 to 135, and so on till 150 to 155. Now while I am constructing these class intervals, I have to understand that these class intervals are exclusive in nature. What do I mean by that? What I mean is that here in 120 to 125, we are putting all the observations which are greater than or equal to 120, but strictly less than 125. So therefore the observation 125 will be counted here in this class interval and not in this one. Okay, and similarly I'll go till the end. So the maximum observation, which we had 150 in our data, is going to go into the last class interval, which is 150 to 155. Now before I go on to find the frequency of these class intervals, it is important to see a very important thing is class marks. So what is a class mark? Class mark is you add the lower limit. So for instance, if I take the class interval 120 to 125, my lower limit is 120, upper limit is 125. So the class mark is sum of the lower limit plus the upper limit divided by 2. Therefore, it becomes 120 plus 125 by 2, which is equal to 122.5. Similarly, I construct the class marks of all the class intervals. The importance of this class mark is that this 122.5 represents the class interval 120 to 125, assuming that frequencies are uniformly distributed over this class interval. So whenever in future I am going to find maybe mean, median, mode, or any skewness, kurtosis, I am going to just look at the values of class marks, which I will represent by small xi, and the values of frequency, which I am representing by small fi. Now I meaning I is 1 means of the first class interval, I equal to 2 means of the second class interval, and similarly there are 1, 2, 3, 4, 5, 6, 7 class intervals, so I is going from 1 to 7. Now once I have constructed the column on class mark, then I go on to construct the column on frequency, and it is very simple to find out the frequency. What we do is we go to the data. So let me go to the data. Here look at this part, how many are between 120 to 125. 120 belongs to that. then you have 123 belongs to 120 to 125 and 124. So there are 4 in total observations which are belonging to the interval, class interval 120 to 125. I will again mention this fact that 125 will not be counted in this interval, it will go to the next interval. So having said this, now I have clearly defined this table, and this table we will call it as the continuous frequency distribution of variable capital X. Once I have made the frequency distribution, then we can graphically represent the frequency distribution of capital X, and at times we have noticed that it is always better representation, in the sense it is more visible when you write a number, it is less visible than when you write or when you draw a diagram. So let us look at what is the graphical representation of a continuous frequency distribution, and that graphical representation is through the histogram. The thing is that so how do I go on to make the histogram? So first I will mark the class intervals on the capital X axis and the frequencies which we have found on the capital Y axis. Then we must ensure that scales for both the axes have to be same. Then we will draw rectangles with bases as class intervals and corresponding frequencies as heights on the class interval. The height of each rectangle is proportional to the corresponding class frequency if the intervals are equal. If the intervals are not equal, there is something special you have to do, but here I am assuming that class intervals are of equal width, and there you will just draw or erect a rectangle of height proportional to the frequency of that particular class interval on Y axis. And then we have to ensure that these rectangles are drawn with no gaps between them, one thing. Secondly, the width of the rectangles is equal to the width of the class interval. So therefore they will be same, because here we have assumed that the width of the class intervals are same. What happens when the class intervals are not of the same width? Then we follow the entire above procedure, except that we will now plot the height of the rectangles as proportional to frequency density. So where the frequency density of a class interval is obtained by dividing the class frequency by its class width. So here the class interval, all the class intervals are not going to be of the same width. So what we will do is, for a particular class interval, we will look at the class frequency of that interval and divide it by the width of that class interval. So we will have to, that means we have to make one more column in the above table, which is the frequency density. We have made the column of class interval, we had made the column on class mark, we have made the column on frequency, but if the class intervals are not of the same width, then we have to further make one more column, which is the frequency density. And here in this, when we draw the histogram for such a frequency distribution, I will plot the class intervals on the capital X axis and the frequency density on the capital Y axis. So this kind of figure will be get. We have just constructed, I have just made this histogram on the class frequency distribution that I have already considered a while ago. So there, so you can see that here class intervals are plotted on the X axis, and you must remember to write the what these class intervals imply. Here they imply height, it might imply weight, it might imply marks. So whatever the class intervals imply, there you must write the name of those that variable here. It is very important, otherwise the figure doesn't make much sense. And similarly on Y axis you will always plot frequency, so you must write frequency here. So what we have done is we are making a, so as I said that we had considered 7, so 1, 2, 3, 4, 5, 6, 7. So there are 7 rectangles that we have drawn, since we had constructed 7 class intervals, and there the first class interval had the frequency 4. So you can see that over 120 to 125, this blue rectangle that I am erecting over it is of the height 4. Similarly, these 3 were of height 6. Okay, so and this was 11, and then last one was maybe 3 or I think it was 2. Yeah. So here this is, and all these rectangles are connected to each other. okay, and they will of course be of the same width because the class intervals are of the same width. So, this is the one of the very appropriate representation of a continuous frequency distribution of capital X. Then we can move on to one more representation which is called the frequency polygon. Okay. Now, in frequency polygon, what we do is, first let me just give the procedure, and then when I come to the graph, then we can talk about it a little bit. So, here we will mark the class marks of each class interval on the horizontal axis. So, instead of class intervals, now I am going to mark the class marks of each class interval on the horizontal axis, and I am going to mark the frequency of the class on the vertical axis. What we are going to do is, we are going to plot the frequencies corresponding to class marks of respective class intervals. In addition to the given data, we will notice that there are two frequencies which are coming out as 0. So, these are the frequencies which correspond to the class mark before the first class interval, which was 120 to 125, and after the last class interval, which was 150 to 155. The reason being that we assume, since our data is starting from 120, so we assume that all the class intervals before that have frequencies 0. So, therefore, when we consider the interval 115 to 120, then that frequency will mark it as 0. Okay. And similarly, when we consider the class mark corresponding to the class interval 155 to 160, that also we will mark it as 0. So, that means we will locate the class mark of 115 to 120 and put the frequency as 0, and we will locate the class mark of the one interval after the last interval which we had in our distribution, which is, we will go from 155 to 160, and then we will put the frequency as corresponding frequency as 0. So, then see, this is the kind of thing that we are, this is the kind of the data that we have. So, here I am going from 120 to 125, frequency is 4, then 100. So, that means I am looking at the class marks here. This is what we are going to plot on the x-axis, and this is what we are going to plot on the y-axis. But as I told you, before this 120 to 125, if there would have been a class interval, it would have been 115 to 120, and then the class mark would have been 117.5, and I would put the frequency as 0 there. Similarly, here after this last class interval, I will have another, if there would have been another class interval, it would have been 150 to 155, and of course, there the class mark would have been 152.5, and I will put the frequency as 0. So, I am going to plot the frequency polygon keeping this in mind, and this we must always keep it in mind. So, this is what a freehand curve that you obtain. So, as I told you, 117.5 corresponding to that class mark, frequency is 0, and then you just keep on plotting the frequency of corresponding to 122.5, which was 4, and then 11, and then 6, and then and then we go finally to last class interval, which we had taken 155 to 160, whose class mark was 152.5, and there again the frequency becomes 0. So, frequency polygon is in some sense starting from some point on the axis and ending on another point on the x-axis. Again, here these are the class marks and these are the frequencies. So, this is again, sometimes people feel that why should we draw those bars and continuous. It is just enough if we just plot the class mark and the frequency on the graph and connect it by the freehand curve, and that we will call it as frequency polygon. So, this is a frequency polygon of distribution of heights of individual, which we represented by variable x. Now, having said that, we move on to the next topic, which is the measures of central tendency or averages. Now, before I talk about what these mean, I will just cite an example. Yesterday I was reading a news, and there it said that the average height of Indian male as per the latest figures in 2021 is 5 feet 8 inches, and the average height of Indian females is 5 feet 3 inches. Now I am sure you must be also looking at these figures in the newspapers. This averages comes very often in the newspapers if they refer to any data, and you will also when you look at your own results, it is CGPA, the cumulative grade point average. So what it is doing, it is taking the grade points of all the subjects that you have in your course, and it is dividing by the summing those grade points and then dividing it by the total number of subjects that you have. So grade point average is a very CGPA is a very well known thing that we have in our results. So there also you have, on the onset, you have already started talking about the averages. So here under the measures of central tendency, we call it as measures of central tendency or just the averages. Okay, so here every average is the value of the variable. As I said, first we have a variable under study. That is important. First we have a variable under study and then we define its average. So average is the value of the variable which is representative of the entire distribution. So what I mean to say is, when I say the average Indian male height is 5 feet 8 inches, it doesn't mean that every male is of height 5 feet 8 inches. But what we mean to say is that generally the people who will Indian males, if you look at, they will be somewhere in the neighborhood of 5 feet 8 inches. And so therefore that 5 feet 8 inches represents the height of the Indian males. Similarly, you can have many more examples. Now, average is not only related to the arithmetic mean. That the first thing that comes to our mind is that average is the arithmetic mean. No, there are very many, rather 5 measures of central tendency or 5 averages that you can define, and there is different usage for each of the average that you use. So here the following are the 5 measures of central tendency. First is the arithmetic mean, then median, then mode, geometric mean and harmonic mean. We will today discuss little bit more in detail about the arithmetic mean. Before I go on to do that, I would like to first just give you certain ideas that a particular measure of central tendency should have. In the sense, whenever we use any particular average, they have certain merits and they have certain demerits. So these merits and demerits are counted on the basis of certain ideas that they must possess. So the Professor Yule defined the following requisites of an ideal measure of central tendency. He said that the measure of central tendency should be rigidly defined, it should be readily comprehensible and easy to calculate, it should be based on all the observations, it should be suitable for further mathematical treatment. The 3 properties I am sure are already clear by what I have said. The 4th property says that suppose we are given averages of 2 different series and I want to obtain the average of the combined series. Then what this property says is that we don't need to recompute the average. What we can do is we can locate the average of first series and locate the average of the second series, and then the average of the combined series can be obtained in terms of average of first series and average of the second series. So that is why this means that we are given the averages and sizes of more than one series. Again, series don't need to be of the same size, they can be of different sizes. Then we should be able to obtain average of the combined series by using these values. In fact, the property of arithmetic mean, I will talk about it later in my lecture, where I will show that arithmetic mean possesses this property, that is, arithmetic mean is suitable for further mathematical treatment. Then it should be affected as little as possible by fluctuations of sampling. These are the 5 properties which were laid down by Professor Yule. In addition to these 5 properties, the one more desirable property which is not due to Professor Yule is that it should not be much affected by extreme values. Extreme values means, suppose we have a data and generally all the values are lying between say 100 to 170, but there are 1 or 2 which are lying like 250 and 275 and some of them as low as maybe 74 or 48, then they look like an outlier. They are very extreme value and you have that in the data. So what our measure should have is it should not be much affected by the extreme values. So the the 5 measures that I just discussed so far, all of them do not possess all the 6 properties that I have just discussed with you. We will show one by one when we take up the averages, then we will discuss that which measure average satisfies which how many properties of professor which were laid down by the Professor Yule. And in this matter, let me just say that arithmetic mean is the one which is going to be is going to beat all the other averages, because it is going to satisfy most of the properties, rather all the properties which are defined by Professor Yule, except the last property, which is that it should not be much affected by extreme values. Now, arithmetic mean, so let me just first start with the first measure of central tendency, which is arithmetic mean or simply mean. Let's get down to the definition. It is a measure of central tendency of a finite set of observations. Specifically, it is the sum of the observations divided by the number of observations. So, suppose you have 10 observations, you will sum all the 10 observations and you are going to divide it by 10. If you have 15 observations, you are going to add all the 15 observations and then you are going to divide it by 15. In the mathematical notation, we will denote these observations by small x1. So, let x1, x2, so on xn be small n observations on a variable capital X. Then mathematically we can define arithmetic mean of capital X as follows. X bar is equal to 1 upon small n summation I equal to 1 to n xi. Now, this sign is coming up for the first time, which is the capitals. You can see it's a sign for the summation. And how do I elaborate or how do I expand this summation? This summation means that there is a running variable over which the summation is expanded. So, here the variable is I. I is taking values from 1 to n. So, that means first I will start with the value of I as 1. Then my x will become x1. Then plus, then I will become 2, x2 plus x3 plus x4 and so on plus xn. This is, so this summation xi, I going from 1 to n is equal to actually x1 plus x2 plus x3 plus so on plus xn. And this will represent the sum of all the n observations. And then we have to always divide it by the total number of observations, which is small n. This definition works when my data, or when we have a frequency, when we have just the raw data with us. That means we do not have frequency distribution, or the grouping of the variables is not done. It is just that you are given just 10 marks and I have to obtain the average of 10 marks. So, I will just add all the 10 marks, then my summation will go from summation I equal to 1 to 10, because now there are 10 observations xi. This is just a notation. You can use yi, you can use small zi, you can use any variable. So, I am using here xi. So, it will be x1 plus x2 plus x3 up to so on plus x10. Upon, now n will become 10 upon 10. When we, instead of a raw data, if we have a data which is grouped into the frequency distribution. So, whenever we talk of frequency distribution, immediate two things come to our head. First is a value of xi and the value of fi. Whenever I have a discrete frequency distribution, then small xi will denote the value of the variable capital X and small fi will denote the frequency of the ith value of capital X. So, here then we will assume that n values of capital X are given, distinct values of capital X are given, which is x1, x2 up to xn, and their corresponding frequencies are given, which is f1, f2, f3 up to so on fn. But in case we have continuous frequency distribution, in that case I am going to have now the continuous class interval, and then here small xi will mean the class mark of a particular class interval and small fi will mean the frequency of that particular class interval. So, then in that case my I will be going from 1, 2 up to so on n, that is n number of class intervals I am considering. So, in that case the formula becomes x bar, which is equal to x1 f1 plus x2 f2 plus so on xn fn upon f1 plus f2 so on plus fn. So, which I am representing it by summation I equal to 1 to n xi fi upon capital N, where capital N is nothing but the sum of all the frequencies, which is the total number of observations that we have. Thank you everyone for listening to this lecture on arithmetic mean and continuous frequency distribution.